Hello, welcome to lecture 22. In this lecture, we're going to talk about the motion of charged particles in a magnetic field when the velocity is perpendicular to the field. The video playing in the background is a screenshot of a simulation showing the right-hand rule that you use when you know the direction of the current loop to find the magnetic field created by that current loop. We used that a little bit in the last lecture, so I thought this would be a tiny bit of a good review.
Let's think about what happens if we have a positive charge moving in a magnetic field. Let's say our positive charge moves straight up and our magnetic field B is into the page. So let's apply our right-hand rule to find our force. Put your thumb in the direction of the velocity, points up. Put your index finger in the direction of magnetic field into the page or into the screen. Extend your middle finger and you should see that your middle finger points towards the left. So that's the direction of the magnetic force. So now if we look at this, we have a force to the left while something is moving straight up. The force and the velocity are perpendicular. That tells us that the force can only change the direction of the velocity. It can't change the magnitude. So our particle is going to start to drift to the left as it moves upwards at the same time. So as our particle has moved along a little bit further, now its velocity points up and to the left a little bit. If we do our right-hand rule, we see again that our force is perpendicular to the velocity. If you have a look at that, you should see that it's starting to point right towards the center of the circle. So when we have a force that's perpendicular to a velocity, this should be familiar from a Physics 1020 or 1050 course, this is the case for circular motion, and that's what happens with our charged particles. So FB is equal to QV cross B. When our V and our B are perpendicular, we get this special case of circular motion. So if the magnetic force is a result of the cross product between V and B, it means that our magnetic force is perpendicular to V, and our magnetic force is also perpendicular to the magnetic field. So it's perpendicular to both. When it's perpendicular to the velocity, that's the case for circular motion. And when we have charges moving in a magnetic field, we give that a special name and we call it cyclotron motion. So cyclotron motion is circular motion of a charge in a magnetic field. We can do a Newton's second law analysis. We know that the sum of the forces on our little charged particle is mass times acceleration. We're going to assume that our particle is small so that gravity is not a significant force. That means the only force we'll think about will be our magnetic force. So magnetic force is mass times acceleration. Magnetic force is Q times V times B sine theta, but theta is 90 degrees because V and B are perpendicular. That leaves us with QVB equals mass times acceleration. In circular motion, instead of saying acceleration, we can say V squared over R. And we can solve this equation for R equal to m times V over Q times B. This is the radius of a path of a charged particle in a magnetic field. The picture I've got here comes from your textbook. What's going on here is that there's an electron beam being shot in a little chamber of gas. So this is a chamber of gas. The bright blue ring that you see, so this ring right here, this is our electrons moving in a magnetic field. The coils on the outside, they maintain a magnetic field in that chamber of gas. So our charged particles move in the magnetic field, and then the electrons, they collide with the gas in our chamber and it emits energy as light. That's why we're seeing that glowing blue ring. So we can actually see the cyclotron motion of those electrons. One bonus theory question I'm going to ask, I'm not going to answer it. You can talk about it in the discussion groups or you can reach out to me. How do you find the work done by a magnetic force? So see if you can figure out what that is. In this example, we have an electron moving in a half circle. Its initial velocity is up and the path it follows has a diameter of 10 centimeters or a radius of 5 centimeters. We're asked to find the magnetic field that makes the electron travel in this path. So let's start by finding the direction. To find the direction, we'll notice that we know the velocity. We can sort out what the force has to be. Then we can use our right-hand rule to find the magnetic field. In our right-hand rule, our thumb is velocity, our index finger is magnetic field, and our extended middle finger is the force. If you know two of those ingredients, you can always find the third. Let's start with the direction of the force. The electron travels a circular path. So in circular motion, the direction of force is always towards the center. So I drew a force vector towards the center here. Now I'm going to apply my right-hand rule. There'll be a little bit of hand twisting, and you should do this along with me. So your thumb goes with your force, and then you get all your three fingers in order. And now twist your hand until your middle finger matches your force. Should look more or less like this. So look at what your index finger is doing, and your index finger should be coming out of the page towards your face. That would at first tell you that the magnetic field is out of the page towards you, but you have to remember that an electron is a negative charge, so you have to rotate your answer by 180 degrees. So the direction of the magnetic field is actually into the page. Next, we'll find the magnitude of the magnetic field. Let's work on finding the magnitude of the magnetic field now. So Newton's second law says that the sum of the forces is mass times an acceleration. Electrons are very tiny, so the gravitational force on them is very small. That means that our net force is really just due to the magnetic force, equals mass times acceleration. Magnetic force is QV cross B. V and B are perpendicular, so we'll say QVB times the sine of the angle between them, but that angle is 90 degrees because V is up and B is into the page. Those are perpendicular. Is mass times acceleration. When things go in a circle, the acceleration is V squared over R. Sine of 90, that's 1. We'll divide both sides by V, so we get rid of one of those. And we see that B is equal to M times V over Q times R. Okay, we want to find the magnitude of the magnetic field. So that's going to be the mass of the electron times its speed divided by the magnitude of the charge divided by R. So we've got 9.11 times 10 to the minus 31 kilograms times the speed 1.41 times 10 to the 6 meters per second divided by the magnitude of the charge, which is 1.6 times 10 to the minus 19 coulombs. We're not including the negative sign because we're just trying to find the magnitude of the field, times the radius of the path. The diameter is 10 centimeters, so the radius is 5 centimeters or 0.05 meters. So the magnitude of our magnetic field is 1.61 times 10 to the minus 4 teslas. And then we'll just finish by writing our magnetic field as a vector, 1.61 times 10 to the minus 4 teslas into the page. If you decided to put on a coordinate system and use X, Y, or Z, that's fine too. You can also do that. For part B of this problem, we're asked how long does it take for the electron to move from point A to point B? Here we'll go back to some straightforward kinematics. Speed is distance over time. The distance traveled is a half of the circumference, or a half of 2 pi r. Divide that by t. So if we want to solve for t, it's going to be a half of 2 pi r, or just pi r, divided by the velocity. So pi times 0.05 meters divided by 1.41 times 10 to the 6 meters per second gives us a time of 1.11 times 10. My, that looks like a bit of a mess. Try that again. 1.11 times 10 to the minus 7 seconds. That's pretty fast, but our little particle is moving very fast, so it makes sense that the time wouldn't be very long. As a homework problem, let's assume that we don't have an electron anymore. Let's assume that we have a proton. So what magnetic field would make a proton follow this path? I'm not going to do a video for it, but I will write up a solution and post it. This problem is almost exactly like the last one, so I'm not going to work through this in a video, but I'll leave you to read it, and I will write out the solution and post it if you want to check your answer. In this example, we have an electron. Let's say our electron starts here somewhere at the beginning. An electron first passes through crossed electric and magnetic fields. So our first region here, this has two fields. It has E and it has B. The electric field is established between the two gray plates that you see. The magnetic field points out of the page. You can see that because of the dots. It says only electrons with speed 1 times 10 to the 7 meters per second pass straight through. Because this selects which particles can pass straight through, this device with the crossed electric and magnetic fields is called a velocity selector. So it chooses which particles can pass through. Okay, after our electron passes through our velocity selector, it goes into a second magnetic field where it strikes the sensing plate in 2 nanoseconds. The sensing plate is right here on the back. So part A, draw the electron path from start to finish. So our electron comes in, it's moving to the right, goes all the way through. It does not deflect up or down, because the problem says these pass straight through. So it's going through with our velocity there. As soon as our electron gets to this region with only the magnetic field that points into the page, it has a velocity that points forwards, and it starts to feel a magnetic force. If you do your right hand rule, you'll point your thumb with your velocity, that's to the right. You'll put your index finger with magnetic field, that's pointing straight into the computer screen. And when you stick up your middle finger, you should see that it points up. That would be the direction of a force on a positive charge. Of course, our electron is negative, so we have to flip it by 180 degrees, which says that our magnetic force on our electron in this field points straight down. That tells us that the path of the electron is going to curve down. It's going to make a circle where it goes downwards. And here's where it hits the plate and it lights up and it makes a mark. Okay, so that's part A, that's the electron path. The next parts we'll start to analyze and find the field and the radius and the second magnetic field. We've got part A all done now. Next we'll move on to part B. What is the electric field? We remember, of course, electric field is a vector, so we'll have to find magnitude and direction. Redraw a tiny bit of the diagram here. Got our two plates and our magnetic field that points out of the page. We've got our electron that's moving forward with some velocity. The problem says that the electrons go straight through. If the electrons go straight through, that tells us that the acceleration has to be 0. If the acceleration wasn't 0, they would deflect up or down. If the acceleration is 0, then the net force has to be 0. And if the net force is 0, then the magnetic force plus the electric force has to be 0. We're going to neglect gravity because electrons are really very light. So if our magnetic and electric forces sum to 0, it tells us that our magnetic forces and our electric forces must be equal and opposite. Okay, we can work with that. Let's sort out the magnetic force direction first. So our charged particle is moving to the right. You put your thumb to the right. Your magnetic field is out of the page, so you take your index finger and you poke it towards yourself. Your extended middle finger should point down. That would be the direction of the force on a positive charge. Our charge is negative, so the magnetic force points up. There's our magnetic force. Our electric force has to be opposite so that they cancel, so our electric force points down. Okay, let's apply our equation now that the magnitudes of the electric and the magnetic force are opposite. So the magnitude of FB equals the magnitude of FE. The magnitude of a magnetic force is the magnitude of the charge times the magnitude of the velocity times the magnitude of the magnetic field times sine of the angle between V and B, that's 90 degrees, equals the magnitude of the electric force, which is the magnitude of the charge times the magnitude of the field. We've got a Q on both sides, so they can cancel. Sine 90, that's just equal to 1. So we're left with the magnitude of the electric field is equal to the velocity of the particles. Why don't I write the equation? Equals V times B. So 1 times 10 to the 7 meters per second times the magnitude of the magnetic field. We're given that that's 1.25 Teslas. So altogether, the electric field is 1.25 times 10 to the 7 newtons per coulomb. Of course, we're not finished because electric field is a vector. So how are we going to get the direction of our electric field? Let's remember that Fe is equal to Q times the electric field. Our charge is minus the fundamental charge. So our force and our electric field are in opposite directions. That's what that negative sign tells us. So Fe and E are opposite. So we know that our Fe points down because it has to balance with our magnetic force. That means that our electric field must point up. So there's our result. Our electric field is 1.25 times 10 to the 7 newtons per coulomb, straight up, or J hat, if we put in a coordinate system where positive x is to the right and positive y is up. Okay, there's part B done. Next, we'll talk about what happens in the second magnetic field. So next we can move on to part C. What is the radius of the path when the electron is in the second magnetic field? So what's going on over here? Well, we know some stuff over here. The velocity of our electron is 1 times 10 to the 7 meters per second. And we know that the time it takes is 2 nanoseconds. If we think about the fact that velocity is distance over time, and our electron travels through a half of an arc, that's 1/2 of 2 pi r, divided by time, r is the radius of the path, that's what we're trying to find. So 1/2 cancels with our 2, and then we can go ahead and solve for r. r is equal to v times t divided by pi. Put in 1 times 10 to the 7 meters per second for v, 2 times 10 to the minus 9 meters per second for t. Divide that by pi, we get 6.37 times 10 to the minus 3 meters, or 6.37 millimeters. Okay, there's C done. Now we'll do part D and figure out what is the strength of the second magnetic field. For our last part now, to find the strength of the second magnetic field, we write Newton's second law on our electron when it's in the field. Sum of the forces is m times a. Assuming the gravitational force is small compared to the magnetic force, then the magnetic force is m times a. Magnetic force is Q times V times B. This is in our second field, so I'll call that B2, equals m times V squared over r. We're trying to find B2, so B2 is m times V squared divided by Q times r. Since we're trying to find the magnitude of B2, we'll use the magnitude of our charge. Okay, m is the mass of our electron, that's 9.11 times 10 to the minus 31 kilograms. V is its speed, 1 times 10 to the 7 meters per second. Divide that by the magnitude of the charge, 1.6 times 10 to the minus 19 coulombs, divided by the radius of the path, which we found in the previous part. Put all that through the calculator, we get 8.94 times 10 to the minus 3 teslas. And then since magnetic field is a vector, we do have to write it as a vector. So you can say that it's into the page, or you can say that it's in the minus k hat direction. So far, we've only discussed what happens if the velocity is perpendicular to the magnetic field. So in my picture here, the velocity might be in the negative z direction. I'll call that v perpendicular. But what if the velocity has a component that's also parallel to the magnetic field? So what if it has a component all in the x direction? Well, we know what the v perpendicular does. That causes circular motion because the magnetic force is perpendicular to both. But what about the parallel component of the velocity? Well, if magnetic force is qv cross b, any part of the velocity that's parallel will have a zero resultant force. That means that velocity won't change and it will just drift in that same direction. So you'll get a circular motion with a parallel drift. What you'll get is that your charge will actually move in a helical shape. I've got a real simple demo to show you about that.
In our next little demo, let's look at what happens when your velocity has a component perpendicular to a magnetic field and parallel to a magnetic field at the same time. So let's assume that my tennis ball is a charged object and I've got a magnetic field that points straight down into the floor. If I give my tennis ball, my charge, a little bit of velocity that's perpendicular to that field, it's going to start to go around in a circle. Okay, we've already studied that part and we said QVB equals mv squared over r, and we get the circular motion because the magnetic force is perpendicular to the velocity. But what if my velocity also had a component that's pointed up? I'd get the circular motion because I have a magnetic force pointed towards the center of the circle, but if I also had a component of velocity that pointed up, then my tennis ball would move up as it went in a circle. My resultant motion would actually be a helix.
And the application of those charged particles moving in a circular path when they encounter a field is actually the northern lights. I've only ever seen these once, and they weren't kind of super bright. It was here in Newfoundland, so I wasn't that far north. My mom and dad, who used to live up north, they saw them a bunch of times and said they're spectacular. It is definitely on my to-do list in life, is to see the magnetic or see the northern lights. Or southern lights would be cool too. So anyway, what happens is our sun, when it has solar flares, and that happens all the time with solar storms, in a solar flare, the sun shoots off huge amounts of charged gas particles. So they're big streams of charged particles coming out from the sun. And they're traveling through space at really high speeds. These particles head towards the Earth. They head out in all directions. Some of it gets veered away from the Earth just with the magnetic fields, but some of it gets trapped and follows along the magnetic field lines. As they follow along the magnetic field lines, they're making these circular paths as they're coming down around the field lines, and that's the magnetic force makes them go in a circular path. As they're moving through the atmosphere, these gas particles, they actually collide with the air molecules. So they collide with the oxygen and the nitrogen. When they have these collisions, they give out large amounts of energy, which we see as those colored lights. So it makes the air molecules glow when the gas particles run into it. So that's pretty spectacular. This is an interesting experimental problem. If we'd like to measure the charge to mass ratio for a particle, we can do that. So if we start our particle at some area of a high potential, we accelerate it towards an area of low potential. So it's moving in an electric field. So we have a positive charge, we release it here, it will start to move to the right. It will get over to the second plate while it's still moving to the right. And then we put a magnetic field over here. We have a charged particle moving in a magnetic field. The direction of the magnetic force when you do your right-hand rule will be straight up, so it will move around in a circle with radius r. The potential difference between the plates is delta V. So if we measure R and we measure delta V and we make a graph, we should be able to figure out the charge to mass ratio. So let's start that analysis. The very first part, let's see if we can figure out how the speed of the mass when it reaches the second plate, how is that related to the potential? So it starts over here at the left plate. That's got high potential. It moves towards the second plate. That's got low potential. Positive charge will move with electric field, and we know electric field points from high potential to low potential. So our left plate is initial, our right plate is final. So E initial equals E final. Initial energy is kinetic plus potential. Final energy is kinetic plus potential. Then we'll fill in that kinetic energy is a half m v initial squared plus q times v initial equals k final 1/2 m v squared. To keep with my notation in the diagram, instead of writing vf, I'm just going to write v plus q times our final potential. Our charge is not moving initially, so that's 0. So we see 1/2 m v squared equals q v initial minus q v final. Our initial potential is bigger than our final potential, so this is the same as q times delta v, where delta v is a positive number. Okay, let's solve this for our velocity. So our velocity v is going to be 2 times q times delta v divided by m, take the square root. Okay, there's the velocity of our charged particle with charge q and mass m. Okay, next part, let's sort out what happens to it when it's in the magnetic field. Let's use our Newton's second law. So for the second part, so this is our first part, this is in the electric field. Why don't we go on to a fresh slide for the second part? For our next part now, let's look at what's happening over in the region with the magnetic field. We'll write our Newton's second law. Sum of the forces is mass times acceleration. Assuming our particle is small, we only need to worry about the magnetic force. Magnetic force is QVB. They're perpendicular, so the angle between them is 90 and sine of 90 is 1. Mass times acceleration is m times v squared over r. I'll divide through by v on both sides. Our problem is talking about doing a graph of r squared, so I'd like to solve this equation for r. R is equal to m times v over q times b. Okay, the next thing I'm going to do now is I'm going to take my expression for v and I'm going to pop it into my expression for r. Ultimately, that's going to give me an expression for r that has a delta v, or a change in potential, in it. So r is equal to m times v, which is the square root of 2 times q times delta v over m, divided by q times b. I'm going to deal with my numerator first. I've got an m on top, a root m on the bottom. So I can bring it inside. That would be m squared times 2 times q times delta v over m, divided by q times b. So that's equal to the square root of 2q delta v over, oops, sorry, shouldn't have been a fraction. It's the square root of, so I've got an m squared on top, m on bottom, so one of those cancels. 2qm delta v divided by, in my denominator here, I've got q times b. I'm going to say that's the square root of q squared times b squared. So that means this q can cancel with one of these q's, and I'm left with r is equal to the square root of 2 times m times delta v over q times b. So there's an expression for my potential and my radius of my circle related. My question says I'm going to plot r squared versus delta v. So my next step, I'm going to square both sides of the equation so that I have the things that I said I was going to plot. My problem says I'm going to plot r squared versus delta v. and that I'm going to get a straight line graph, which I know the slope of. So I'd like to get an equation now for r squared. So I'll square both sides. R squared equals 2 times m over q times b times delta v. Okay, there's my equation. The slope of a straight line graph, you can either compare it to y equals mx plus b, or you can think of your rise over run from high school. It doesn't really matter. So slope is equal to r squared divided by delta v. From our equation, r squared over delta v is 2 times m over q times b, or 2 over b times m over q, just to put some brackets around the term there. We're asked to find q over m, but we know what the slope is, so and we know what the magnetic field is, so let's fill in the things that we know. So our slope is 1.04 times 10 to the minus 6 meters squared over volts. That equals 2 over the magnetic field, 0.20 teslas, times m over q. We'd like to find q over m, so q over m then will be 2 divided by 0.200 teslas, and then that's going to be divided by 1.04 times 10 to the minus 6 meters squared per volts. Put that through the calculator and we get a charge to mass ratio of 1.04 times 10 to the minus 5 coulombs per kilogram.